Hey guys, congratulations on making it to the last test of the year. Oh, how very bittersweet. Before I get into the ins and outs of what content-wise to expect on this test, please do not forget unit conversions. There were still many issues with that in test 5, so do you happen to know what micro means? Do you happen to know what symbol micro is? Do you know what milli is? How about kilo? It really should be like the back of your hand. All that aside, we'll start talking about magnetic field. The basics of it are that no magnetic monopoles ever exist. So unlike electric field, where you could have a single positive charge or a single negative charge, any sort of a magnet is going to have both a north and a south pole. The convention for field lines is that they exit the north pole and enter the south pole. The symbol for magnetic field is B, and it is measured in units of Tesla as the base unit. 1 Tesla is actually a really, really strong magnetic field, so a lot of times you're going to encounter things like millitesla or microtesla. Make sure you know the difference between those two. Now, what makes magnetism really interesting is its relationship to electricity. If I just have a single charged particle flying through a magnetic field, I use what's called a vector cross product to solve for the force that this charged particle experiences. Don't forget, a cross product is a means of multiplying 2 different vectors to produce a third vector called the resultant. Now, every vector, the force resultant included, has a magnitude, that's just a strength, a value, and it has a direction. You can find the magnitude as the first vector times the second vector times the sine of the angle between them. In this case, that will come to QVB sine theta, where theta is the angle between the velocity and the magnetic field. To find the direction, you can use the first right-hand rule. Anytime you are faced with a cross product, which in this unit is any time you are faced with a force. Start by karate chopping in the direction of the first vector. In this case, that'll be velocity, because it's QV cross B, not B cross QV. So karate chop, keep your palm open, point all your fingers in the direction of the velocity. Then you're going to have to rotate your arm, keeping your fingers pointing straight forward in the direction of the velocity, until your palm faces the direction of the magnetic field. That way you'll be able to bend your middle or ring fingers to point in the direction of the magnetic field. When you stick your thumb straight away from your hand, it should be at 90 degrees to your velocity fingers, should be at 90 degrees to your magnetic field fingers. That will be the direction of the resultant vector, in this case, the force. I'm not necessarily going to always give you the velocity and the magnetic field and have you tell me the direction of the force. Sometimes I'll give you force and velocity and have you tell me the direction of the field. Or sometimes I'll give you field and force and have you give me the direction of the velocity. Make sure you know which part of your hand corresponds to what. Here's a helpful little diagram to help you remember that. Your finger, your index finger, is the direction of the velocity. The palm / the middle finger is the direction of the magnetic field, and your thumb is the direction of the force. Make sure you know the difference between up the page and out of the page. A lot of times it helps to actually pick your test paper up in front of you and hold it upright in front of your face. That way, up toward the top of the page is also upward in the room toward the ceiling. Into the page would be away from you, out of the page would be toward you. Make sure you understand these symbols as well. If I just give you a circle and a dot, I expect you know that's out of the page. If I give you a circle with an X in it, I expect you to know that's into the page. Remember, it kind of looks like arrows in all directions. Up, down, left, right, that's easy. Out of the page looks like a little arrowhead pointing toward you. Into the page looks like the feathers of that arrow flying away from you. There's a special case for negatively charged particles. Negatively charged particles are going to feel a force in the opposite direction as their positive counterparts. So when you're dealing with a negative particle, if you see the word negative, see the word electron, remember to either use your left hand or just change the direction by 180 degrees. Now the second vector cross product you faced was the force on a current carrying wire. It's exactly the same equation, except instead of a single charge, the current is a whole bunch of charges, all traveling through this magnetic field. When you add up the individual QV cross B for each and every little charged particle moving, you'll get the total force on that wire being IL cross B. The magnitude is just the two vectors multiplied by each other times the sine of theta, so you've got ILB sine theta, and you're going to use the exact same right-hand rule. But check this out. Not only are current-carrying wires affected by a magnetic field, they also make them. Quick point of clarification, a wire is not going to feel its own magnetic field. A wire will produce a magnetic field that might exert a force on something else, or a wire will feel a magnetic field from something else and experience a force as a result. But a wire is not going to exert a force on itself because of its own magnetic field. Now, to find the magnitude of the magnetic field produced, it's just mu naught I over 2 pi r, where mu naught is 4 pi times 10 to the negative 7 Tesla meters per ampere. This is a value I'll give you on the test, but it's good to know how to work with it. To find the direction of the magnetic field created by a straight wire, you'll use the second right-hand rule. In this case, because the wire is moving in a straight line, the current is a straight line. That gets your thumb. Start with your palm completely open, and then begin to curl your fingers. The direction that your fingers curl as you close your fist is the direction the magnetic field is circling this wire. Now, if the wire itself is looped in a circle, you'll use the third right-hand rule in order to find the direction. But before we get to the direction, let's talk about the magnitude of the magnetic field that it produces. When you have a solenoid, it basically acts like a bar magnet when the current is running through it. You can find the strength of that magnetic field produced by a solenoid as mu naught, that's the exact same constant as before, times the number of loops of the coil, how many times is the wire looped around. L is the length of the solenoid, and don't forget the length of the solenoid is not the length of the wire that makes it up, it's simply the distance from where the loop begins to where the loop ends, and that's it. And I is the current running through it. That's going to be measured in amperes. Now here's a little image of the third right-hand rule. Now that the current is traveling in a circle, that gets the curl of your finger. It's no longer a straight line. When the current was a straight line, it got your thumb. Now that the current is the curl, it gets the curl of your fingers. The magnetic field used to be a circle around that straight wire. Now the magnetic field is in a straight line running through the center of that solenoid, so that gets your thumb. This tells you the direction inside the solenoid that the field is running. Now once you get outside the solenoid, it just acts like a bar magnet. So the spot where the field comes out, that's going to be the North Pole, and where the field goes back in, that's going to be the South Pole. Notice that the second and third right-hand rules are ridiculously similar. You'll only use the second and third right-hand rules when you have a wire creating a magnetic field. When that happens, one of them will be in a straight line, one will be in a circular loop. Whatever's in the circular loop gets the curl of your fingers, whatever is in a straight line gets your thumb. So in terms of right-hand rules, all you have to worry about are vector cross products. Are you finding a force because of a magnetic field? If so, that's a cross product. That'll be the first right-hand rule. Or, are you creating a magnetic field with a wire? If so, that'll be the second or third right-hand rule. And that's it. One last bit of magnetism we gotta cover is Faraday's law. Not only do wires with current in them produce magnetic fields, but magnetic fields moving near wires produce a current. Works both ways. To find the voltage produced in a coil of wire, you'll use Faraday's law. Now this negative is kind of pesky. It's only directional. Basically, it tells me that the current produced by a changing magnetic field goes in the opposite direction as you'd expect from the right-hand rule. When solving these problems, I honestly don't mind if you leave this negative off, but I have to teach you Faraday's law with the accepted equation. Now, epsilon is going to be the voltage produced, sometimes called the EMF. N, again, is the number of turns of coil. Change in phi is the change in magnetic flux. So, basically, the magnetic flux has to change in order to produce a voltage. This means you can find B times A times cosine theta at the end, subtract B times A times cosine theta at the beginning. That'll be your change in magnetic flux. And by the way, delta T is the amount of time that it took the magnetic flux to change. Quick summary. How magnetic fields affect wires and charged objects. You've got two force equations. Both of these would use the first right-hand rule, QV cross B and IL cross B. And the voltage generated by a changing magnetic field uses Faraday's law. Now, how wires produce magnetic fields going in the opposite direction. We've got, from a straight wire, B is mu naught I over 2 pi r. And because of a solenoid, it's mu naught Ni over L. Let's stop talking about magnetism and start talking about waves a little bit. Make sure you know what an amplitude is, what a crest, what a trough is, what a wavelength is. Now, a wavelength can get a little bit tricky, because yes, it is a trough-to-trough measurement, or a crest-to-crest measurement, and it's denoted by the Greek letter lambda. But when you're at a midpoint, it'll be not to the next midpoint, but the one after that. The definition of a wavelength is how far a wave travels before it begins to repeat itself. So if I go from crest to crest, if I were to keep going, then I'd experience the same thing I did before, starting to move down toward a trough. If I go from trough to trough and I keep going, I'd start to do the same thing again. But if I go from a midpoint over a crest to a midpoint, if I kept going, I'd go down to a trough, which I haven't done before, so I've got to get to 2 midpoints over before I've achieved a wavelength. Make sure you know the difference between transverse and longitudinal waves. Instead of crests and troughs, longitudinal waves have what are called compressions and rarefactions. Compressions are regions of high pressure, rarefactions are regions of low pressure. This is how sound, for example, works. The period is the amount of time it takes a wave to travel one wavelength. That's going to be measured in seconds. The frequency is how many wavelengths pass by in a given second. So they're exact inverses of each other. Period versus frequency. The wave speed is how fast a wave pulse is moving. That'll be measured in meters per second. And we've already talked about wavelength. So typically what you need to know is that frequency and period are inverses of each other. And you've got this beautiful wave equation, V equals lambda F, that works for each and every type of wave. Now, if two wave pulses meet each other, they will go through what's called superposition. This consists of constructive interference, where a crest meets a crest, or a trough meets a trough, in which case the amplitudes add. Now, if a crest meets a trough, the wave amplitude will decrease. Either way, you're basically just adding the amplitude vectors. If you got two vectors in opposite directions, that's where you subtract. That's exactly what you're doing with interference. Now, after the waves have interfered with one another, they then just pass on through and continue traveling. If you have a string, you can find the velocity of the wave on the string using this equation, where F is the tension, L is the length, and M is the mass. Sometimes you'll see the equation written like this, where that Greek letter mu there stands for the linear mass density. But it's the exact same equation either way it's written. If you continue to send pulses through some sort of a medium, and they reflect and bounce back and interfere with each other, eventually you'll find a frequency that resonates with an object. In order to resonate, a standing wave has to perfectly fit on the object. Standing waves have regions that oscillate between crests and troughs, but don't seem to have forward motion. They consist of nodes and antinodes. Nodes are where it looks like there is no motion at all. Antinodes are where the biggest oscillations between crests and troughs take place. Anytime you've got a fixed end, you always have a node there. So if I were you, I'd probably jot down these patterns right here. Make sure you can tell me, once these patterns are drawn, how much of a wavelength is fitting on the string here, or here, or here. Make sure you're comfortable doing that. When you have open ends, you have antinodes. I'd probably jot down some of these patterns as well. Make sure you can tell me how much of a wavelength fits on each little pattern there. When you have one end open and one end closed, the closed end gets a node, the open end gets an antinode. Make sure you can tell me how much of a wavelength fits in each of these patterns. And by the way, as you do this, you can label it two different ways: the length of the tube or string or whatever is vibrating, and the amount of a wavelength that fits inside of it. Then you can set those two equal to each other. One helpful trick: anytime you go from a node to an antinode or an antinode to a node, there's always 1/4 of a wavelength. You also need to know the speed of sound in air. In case you have some tube of air vibrating, the speed of that standing wave is just the speed of sound. That'll be 331 plus 0.6 times the temperature. We closed off talking about beat frequency and Doppler effect. So if you've got two sources that differ by 15 hertz or less, a beat is produced, and it's simply the difference between the two source frequencies. It's how often it gets quiet and loud again, how often you hear a womp 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 pattern every second. Finally, there's the Doppler equation. Here, you've got a source producing some frequency, but an observer hearing a slightly different frequency. This is because of the motion between the observer and the source. Here, v is the speed of the wave. In a lot of cases, this will be the speed of sound, but it works for light as well, which we'll get to next unit. VO is the speed of the observer, VS is the speed of the source, and FS and FO are the frequency of the source and the frequency of the observer. The hardest part is figuring out whether VO and VS are positive or negative, so draw yourself a picture of the situation, look at the direction the wave is traveling when the observer hears it. That direction will be defined as the positive direction. If VO and VS are in the same direction as that wave, they are considered positive numbers. If they are in the opposite direction of that wave, they are considered negative numbers. There are a bunch of resources for you to look at before this test. On Module 10, you've got your online lessons. Go back and review those. I also decided to post a few magnetic field problems and solutions worked out so you can see an example of a bunch of these equations. On Module 11, make sure you hit those online lessons again. And then under Old Test Solutions and Review, I've got this document right here and last year's test with all the solutions. So hit those up. In addition, you have that textbook linked on the front page of my Canvas course. Also, the internet exists. If something is still slightly confusing to you, Google the heck out of that thing. There's a lot of great resources out there. And don't hesitate to ask me if you have any questions before we come up on this test. Have a good one.